Welcome to my channel Phi Concepts CHM. This video is the second part of the series of electrical properties of metals. Here we will see the drawbacks of Drude's classical theory. First is the heat capacity of electron gas, calculation of mean free path, Weidmann-Franz law, and also we will be seeing about the relaxation time. Heat capacity of electron gas. Classically, all free valence electrons in a metal can absorb thermal energy, but in fact it is not. According to law of equipartition of energy, every free electron has average kinetic energy. So kinetic energy can be given as half mc bar square. Substituting c bar as the root of 3 kT by m, we get the kinetic energy as 3 by 2 into kT. Consider 1 kilomole of metal. If there are Na number of atoms, therefore there will be Na number of free electrons, assuming that each atom contributes one valence electron to the electron gas. Therefore, the total energy of the electrons will be given as capital U is equal to 3 by 2 Na kT. If heat is supplied to a material, free electrons also absorb part of the heat. That is, the electronic specific heat is given as Cv suffix El, that is the electronic specific heat, is equal to du by dt. So we will differentiate U with respect to temperature T. You get 3 by 2 into Kna. Kna from this equation, where K is equal to R upon Na, can be written as, this can be written as R. So you get Cv electron as 3 by 2 into R. Also, specific heat associated with the lattice vibrations is equal to 3 into R. Therefore, the total specific heat for the metals will be the sum of these two specific heats. One due to the lattice ions, the other due to the electrons. So 3R plus 3 by 2R. That is, the specific heat should be enhanced in metals due to the presence of the free electrons. But experimentally, specific heat associated with the electron gas is small. So, the conclusion is that all the free electrons do not contribute to heat capacity. Calculation of mean free path. The classical theory fails to explain the large observed values of mean free path lambda. The resistivity of the metal is given as rho is equal to m upon Ne square tau. From this we get tau is equal to m upon Ne square rho. Also, tau is equal to lambda by c bar. We can calculate lambda as c bar into tau. Experimentally, it is found that lambda is nearly 10 times above this classical value. This is due to the incorrect assumption of classical theory that lambda is independent of temperature. Weidmann-Franz law. It gives a relation between electrical and thermal conductivity. The law states that the ratio of thermal to electrical conductivity is directly proportional to absolute temperature. Heat conduction in solids occur by vibrations of atoms and by free electrons. In the metals, the electrons play a major role. These electrons carry energy from one place to another, that is, from heated part to cooler part. Consider a conductor of uniform cross-section. Let thermal gradient be established. Consider lengths A, B, C, normal to the direction of heat flow. Each of them is separated by a distance lambda. Figure above shows steady state temperature of layers. These are the steady state temperatures given, and these are the thermal energy of the electrons at those respective layers. Excess of energy carried away by the electron from layer A to layer B can be given as dE by dx into lambda. By kinetic theory, number of electrons flowing in a given direction through unit area is equal to 1 by 6 nc bar, where n is the density of electrons, c bar is the thermal velocity of the electron. Excess of energy transported in the direction of heat flow in unit time at layer B is 1 by 6 nc bar lambda into dE by dx. Equation 1. The same amount of energy flows in the opposite direction from layer B, which is given as the same but with a negative sign, minus 1 by 6 nc bar lambda dE by dx. Therefore, the net heat energy transported from A to B is the difference of both 1 by 6 nc bar lambda dE by dx minus of minus 1 by 6 nc bar lambda dE by dx. So we get this as, this is 2 by 6 and hence it reduces to 1 by 3 nc bar lambda dE by dx. Equation number 2. This equation number 2 must be equal to the product of thermal conductivity and temperature gradient. So this is equal to sigma T, sigma suffix T, which is thermal conductivity, and dt by dx, which is the temperature gradient. Equation number 3. Now we will consider n into dE by dx, n dE by dx, which for this we will multiply and divide by dt. So this is n into dE by dt into dt by dx, where dE by dt is the electronic specific heat. So substitute Cv suffix El. Equation number 4. Substituting equation number 4 in equation 3, we get this where dt by dx gets cancelled out, and we get the sigma suffix t as 1 by 3 into Cv suffix El lambda and C bar. Equation number 5, where Cv suffix El is 3 by 2 K, which we had got earlier when we had seen heat capacity, and C bar is equal to square root of 3 kT by m. Substituting this in this equation number 5, we get sigma suffix t is equal to n lambda k upon 2 into square root of 3 kT by m. Equation number 6. This is the equation for thermal conductivity. Also, we had derived the electrical conductivity as n e square lambda upon square root of 3m kT. This is the electrical conductivity. So we'll take the ratio sigma suffix t upon sigma, that is thermal conductivity, to the electrical conductivity, and we will divide both the equations. We get 3 kT into k by 2e square. This can be written as sigma suffix t upon sigma is equal to 3t by 2 into k by e the whole square. Equation number 8. Here in this equation, leaving t, all the other terms are constant. So we see that sigma suffix t upon sigma, this ratio is proportional to capital T. This is the Weidmann-Franz law. The multiplying constant can be written as L. Capital L is equal to 3 by 2 into k by e the whole square. Equation 9. It's called as a Lorentz number, and if you substitute this, equation 8 becomes sigma suffix t upon sigma is equal to L into T. From this you can find the Lorentz number L as sigma suffix t upon T into sigma. Equation 10. Values of L from equation number 9. From 9 we get the theoretical value of Lorentz number, and from equation 10 we get the classical value of Lorentz number. So these values of L from equation 9 and 10 vary, showing L does not agree with the value from the classical theory. The conclusion is that quantum theory with Fermi-Dirac statistics reveals that only electrons near the Fermi level take part in thermal and electrical conduction. Relaxation time. Suppose at a given time t is equal to 0, the average velocity of the electron is denoted as average of Vx suffix 0. At that instant, if the field is switched off, so that the average of Vx tends to 0. That is, the velocity will be randomized due to the electron lattice collisions. Assume that this process follows simplest law of exponential decay, which is shown in this diagram. Here the velocity is decreasing exponentially. So this can be given by this equation. V average of Vx is equal to average of Vx suffix 0 into e raised to minus t by tau. At t is equal to tau, we get average of Vx as V suffix x suffix 0 upon e. So tau is called as a relaxation time because it gives a measure of time that the system takes to relax when a constraint such as electric field is removed. It is the time taken for the drift velocity to decay to 1 by e of its initial value given by the square bracket equation. Thank you for watching my video.